Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It's our second lesson on the last topic of Form 4, which is called electronics. As usual, let me commence by giving the quote of the day, which states that the biggest room in the world is the room for self-improvement. We shall discuss that quote at the end of our class today. So today we are looking at the types of semiconductors, and we are saying that we have two types of semiconductors. One is what we call the intrinsic semiconductor, and two, we have what we call the extrinsic semiconductors. So let's start by discussing what we mean by an intrinsic semiconductor, whereby you are saying that an intrinsic semiconductor is simply a pure semiconductor. So when we talk of pure, we simply mean that for the case of intrinsic semiconductor, the electrical conductivity is not dependent on the presence of impurities. So an intrinsic semiconductor is a pure semiconductor whose electrical conductivity is enhanced by temperature alone. So that simply means that for the case of intrinsic semiconductor, at room temperatures, they are simply insulators, or they do not conduct electricity. However, if their temperature are increased beyond a certain level, then they become conductors. Examples of intrinsic semiconductors include silicon and germanium. So you can see we have the conduction band. Of course, we have a small forbidden gap for the case of intrinsic semiconductor, because remember, it is still a semiconductor. Because remember, in electronics lesson 1, we did say that for the case of semiconductors, the forbidden gap is so small such that electrons can easily move from the valency band towards the conduction band where necessary, or if some certain conditions are met. So at room temperature, intrinsic semiconductors are simply insulators, or they do not conduct electricity. But if their temperatures are increased beyond a certain level, then the intrinsic semiconductors will become conductors, or they will allow electrical conductivity. Now, when an intrinsic semiconductor is heated, or when its temperature is increased, the electrons gain thermal energy, or simply what we call kinetic energy, and move from the valency band to the conduction band. So you can see this is our valency band. Then of course we have the conduction band. In between we have a small forbidden gap. So you can see we have an electron which has escaped from the valency band by passing the small forbidden gap into what we call the conduction band. Remember, when an electron leaves the valency band, it leaves behind what we call a hole. Remember, we said that holes are usually positively charged, whereas electrons are usually negatively charged. So when an intrinsic semiconductor is heated, or when its temperature is increased, the electrons gain thermal energy or kinetic energy, and therefore move from the valence band to the conduction band, hence enabling electrical conductivity. Remember, when an electron moves from the valence band to the conduction band, then it means that electron is going to enable what we call electrical conductivity. Then the conduction in intrinsic semiconductors is because of the both electrons and the holes. Of course, the holes which are left behind by the excited electrons, which have jumped from the valence band to the conduction band. So there is usually this common question that you differentiate between that is conductors and semiconductors in terms of their electrical conductivity. So the first difference between a conductor and a semiconductor in terms of the electrical conductivity is that for the case of semiconductors, and to be specific, the intrinsic semiconductors, their electrical conductivity is enhanced by both electrons and holes. Whereas for the case of conductors, their electrical conductivity is only enhanced by electrons only. Then the second difference between a conductor and a semiconductor is that for the case of a conductor, that is, their conductivity actually decreases with increase in temperature. Whereas for the case of semiconductors, their electrical conductivity increases with increase in temperature, because you can see we are saying that when a semiconductor is heated, and for this case an intrinsic semiconductor, the electrons are going to gain thermal energy or kinetic energy, therefore moving from the valency band to the conduction band, hence improving their electrical conductivity. Next, we look at the second type of semiconductor, which is called an extrinsic semiconductor. Now, what is an extrinsic semiconductor? So an extrinsic semiconductor is simply an impure semiconductor made by adding impurities to an intrinsic semiconductor or a pure semiconductor in order to enhance its electrical conductivity. So the process by which this is done is actually called doping. So that process of adding impurities onto an intrinsic or a pure semiconductor in order to make it an extrinsic or an impure semiconductor so that you can enhance its electrical conductivity, that process is what we are calling doping. Now let's define doping in physics. So doping is simply defined as the process of adding minute or small quantities of impurities to an intrinsic semiconductor or to a pure semiconductor to enhance its electrical conductivity. Now, doping in semiconductors usually results into two types of extrinsic or impure semiconductors. So these types entail, one, we have what we call the N-type extrinsic semiconductor, and two, we have what we call the P-type extrinsic semiconductor. So in the next slide, we are going to discuss these two types of extrinsic semiconductors. Next, we look at N-type extrinsic semiconductors, commonly known as N-type semiconductors. Now, how do we form N-type semiconductors? They are formed by doping a pure semiconductor, that is a semiconductor that has no impurities, or what we simply call the group 4 elements. For example, we have silicon and germanium with a pentavalent. Remember, the word penta means 5. Therefore, when we talk of a pentavalent, we simply mean that an atom that has 5 valency electrons, or what we simply call the group 5 atoms. That is, atoms that have 5 electrons in the outermost energy level, which are readily available to be used in bond formation. Examples of pentavalent or group 5 atoms include phosphorus, antimony, and arsenic. Now, a pure semiconductor, that is, for example, germanium or silicon, or what we simply call the group 4 elements, usually has 4 electrons available for the formation of a covalent bond with 4 neighboring atoms. When a group 5 impurity, or what we are calling a pentavalent atom, for example phosphorus, is added, 4 of its 5 electrons participate in the bonding, but 1 electron has no place to form a bond. For example, in this case, we are using phosphorus, which is represented by a capital P. So, of course, phosphorus is a group 5 atom. Therefore, it has 5 valency electrons. So, you can see this is 1 electron of phosphorus, which is forming a covalent bond with germanium, which is represented by capital G, then small e. Then the second electron of phosphorus is also forming a covalent bond with germanium. Then the third phosphorus electron is also forming a bond with germanium. Then the fourth phosphorus electron is also forming a covalent bond with germanium. But the fifth phosphorus electron has no place to form a covalent bond. Therefore, 1 electron remains being free. So when a group 5 or a pentavalent atom is added, 4 of its 5 electrons participate in the bonding, but 1 electron has no place to form a bond. So this free electron is the one that is responsible for electrical conductivity. So the remaining electron is thus donated for electrical conductivity. Thus, phosphorus, or what we call pentavalent or group 5 atoms, are thus said to be donor atoms because they donate an electron or 1 free electron, which is responsible for electrical conductivity. Hence, they are called donor atoms. Now, the resulting semiconductor is what we call an N-type semiconductor, where N stands for negative charge carrier. So negative charge carrier, because you can see we are having free electrons, and we know that electrons are usually negatively charged. Therefore, the electrons are the charge carriers. Therefore, because electrons are negatively charged, that is why we are talking of the negative charge carrier. Therefore, we can define an N-type semiconductor, or simply an N-type extrinsic semiconductor, as the one in which the majority charge carriers are simply electrons. You can see one electron is remaining freely, and it is not involved in bond formation, and this electron is the one that is responsible for electrical conductivity, but the other four phosphorus electrons are being involved in formation of a covalent bond with germanium. Next, we look at the p-type extrinsic semiconductors, commonly known as the p-type semiconductors. Now, how do we form the p-type semiconductors? They are formed by doping a pure semiconductor, that is a semiconductor that has no impurities, or what we call the group 4 elements, which include silicon and germanium, with a trivalent. Remember, the word tri means 3. Therefore, when we talk of trivalent, we simply mean that an atom that has 3 valency electrons, or an atom that has 3 electrons in the outermost energy level, which are readily available for bond formation. So trivalent atoms are also called group 3 atoms. Examples of trivalent atoms or group 3 atoms include boron, gallium, or indium. Now, a pure semiconductor, for example, silicon or germanium, or simply put a group 4 element, usually has 4 electrons available for the formation of a covalent bond with 4 neighboring atoms. For example, in this case, we are using boron and silicon. So, a group 3 impurity, or what we are calling a trivalent atom, for example, boron, has 3 electrons available for bond formation, whereas silicon has 4 valency electrons. So, when boron fits in the silicon crystal lattice, it will have 1 electron less to complete the bonding, leaving a hole. So you can see we have the boron here, which has 3 valency electrons, whereas silicon has 4 valency electrons, such that when boron fits into the silicon crystal lattice, we'll have the first valency electron of boron forming a covalent bond with silicon. Then we have the second valency electron of boron forming a covalent bond with silicon. Then we have the third boron valency electron forming a covalent bond with silicon. So we are going to remain with a hole on one side of this particular boron, because boron only has 3 valency electron, whereas silicon has 4. So there is going to remain a hole without a boron valency electron, because boron only has 3 valency electrons. So when boron fits in the silicon crystal lattice, it will have 1 electron less to complete the bonding, leaving behind a hole. So this particular hole is the one that will be responsible for electrical conductivity, because it can easily accept an electron. So since a trivalent atom or a group 3 atom, for example boron, creates a hole that accepts an electron, it simply means that boron can be called an acceptor atom, or simply put, trivalent atoms are called acceptor atoms because they easily create a hole that accepts an electron. So the resulting semiconductor is called a p-type semiconductor, where P stands for positive charge carrier, because remember we said that a hole is said or is assumed to be positively charged because it can easily accept an electron. So because a hole is positively charged, hence the word a p-type semiconductor, where P stands for a positive charge carrier. Therefore, we can define a p-type extrinsic semiconductor, or simply put, a p-type semiconductor, as one in which the majority charge carriers are holes, or they are positive charge carriers. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that the biggest room in the world is the room for self-improvement. So the quote is encouraging us not to give up on our dreams whenever we encounter setbacks. We should therefore be ready to try and fail so that we can learn and improve. So the most important thing is to keep perfecting our skills and knowledge until we become experts at whatever thing we choose to do. And lastly, recall that you should be so passionate about improving your own life that you do not have time to hate, judge, criticize, or gossip about other people's lives. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Until next time, this is Kind Tuition Academy. Thank you very much.